Okay, so I picked a few problems from each section in chapter 9 to give you just a little overview of what the problems would look like in my stat lab and also where we're going to go in StatCrunch to solve these problems. So this first one is from 9.1, and the data is interesting. They're looking at 12 international soccer players. So that means that n is equal to 12. And they looked at the maximum weight in kilograms that they could do one repetition of a half squat. So the absolute maximum weight they could do a half squat versus the time it takes in seconds to run a 10-meter sprint. Okay, and so that column is here. If you have to, inside my stat lab, you have to click on this, and when you do that, you get your data table here. Okay, so the first thing they want to know is what the scatter plot would look like. So StatCrunch can do that for us. What we're going to do is click on the box here next to the data, and you're going to go to Graph, and then go all the way down to scatter plot. Now it's going to look a little different just because the we can't really control what the axis looks like, the x and the y, but hopefully you can see that it's C. It looks different, looks a little bit different than D. Both of them are pretty close. You can see for sure that there's no way it's A and B, and then from there you can narrow down. So you can see that my data, it has a downward trend, so it has a negative correlation. We don't know yet how strong it is. I think we're going to do that in the next slide. Okay, so next they ask for my correlation coefficient R. We're going to let StatCrunch do that. So again, you're going to click on the box next to the data. You're going to go to regression and then simple linear. When you do that, you get lots of data. But for right now, we want the correlation coefficient. So that is R, and that's sitting right here. And they want 3 decimal places. So I get negative 0.962. Well, we already knew it had a negative correlation, right? We could see that the data was headed downward. And so as X increased, Y decreased. But we see now that it's a very strong, because that's almost 1, right? 0.962 is almost to 1. And therefore, we're able to answer that we have a strong negative. If that had been a positive number, if R had been positive, then we would have had a positive linear correlation. Then they're going to ask me what that means. Well, what it means is the slope is downward. And so as X increases, Y is decreasing. So I think that's C. Right, so you're looking at the correlation, and basically what that's saying is that the stronger, this is what they were hoping, I think, to find, the stronger the person is, and so the more weight that they can handle on a half squat, the faster they're going to run, which I think makes sense. All right, let's see what's next. The next thing that the problem wants is the critical value. For this problem, we're going to go ahead and use the table that they gave us. So in the original problem, they have this link that says, click here to view the table of critical values for the Pearson correlation coefficient. So we're going to click on that. When we click on that, we get this lovely table right here. And so we do need to know N. Well, we know that we had 12 athletes, so N is equal to 12. And then they told me that down here, they told me that they wanted the significance level, alpha, to be 0.01. So what I'm going to do is come down to where N is equal to 12. I want to be in this second column because I want alpha to be 0.01 or 1%. And Therefore, my critical value is 0.708. I think in the lecture videos, I was trying to get you to do it with a T calculator, which works also, but this table is very convenient. So the critical value is 0.708. Oops, I didn't grab my, hold on one second. Let me go backwards. All right, I had to go grab R. So R is negative 0.962. But before I can compare it to the critical value, I need to go ahead and take the absolute value. So remember, absolute value is distance back to 0 on the number line. And so basically what happens is if you put a negative number inside the absolute value, it becomes positive. Whoops, as I write a negative, sorry, it becomes positive. And that's because it's distance, and distance is we always denote it as positive. So now we can compare that to our critical value. Well, our 0.962 is definitely greater than 0.708. Therefore, the R is greater than the critical value. And so I went ahead and I screenshot this from the resource sheet. It says if the absolute value of R is greater than the critical value, then the correlation is significant. Okay, well, that is true for our case. The absolute value of R is 0.962. It's definitely greater than the critical value of 0.708. Therefore, I'm going to say that there is sufficient evidence and that there is a significant linear correlation. If it had been less than, then we would have answered that there was not enough evidence. Okay, this problem is also from 9.1. In this study, they're looking at 10 students, so that means that n is equal to 10. And they're looking at the number of hours spent studying for a test and then their scores on that test. And they want to know if there's enough evidence to conclude that there is a significant linear correlation between the data and that we're going to use alpha equal to 0.05. So our significance level is going to be 5%. For us in chapter 9, we're always just going to use row equals 0 or row not equal to 0. We're always going to use a two-tailed test. If you go further in stats, you would do different things. But for this class and chapter 9, we're going to stick with this. Remember, rho is the population correlation. And basically what we're testing here is that there is no correlation. That would be the null hypothesis versus that we have correlation. And we'll talk about that at the end of the problem. All right, so the first thing they ask for is the critical values. So what we're going to do is we're going to click on, let me change to green. We're going to click on this box up here that says it's the table of critical values for the student's T distribution. And when we do that, we get this lovely table here. But we have to be careful. On the last problem, they asked for N. For this problem, they ask for degrees of freedom. So degrees of freedom when we're doing two variables like this is going to be n minus 2. So for our problem, it's going to be 8. So we're going to come down here to the degrees of freedom equal 8. We know that we have two tails, and we know that our alpha is going to be 0.05. So we're going to come here to this row that is two tail, come over here to 0.05 and work our way down. If you do that, you come here to 2.306. But because it's two-tail test, I have to have both negative and positive. So when I go to answer here, I would get negative 2.306 on the left side, and then I would get positive 2.306 on the right side. Okay, so those are my critical values, and those are found from the table of critical values. Just be really careful because I got a problem wrong. I wasn't paying attention to the column and I was trying to do n equals 10, but it wants degrees of freedom. So for chapter 9, degrees of freedom is n minus 2. All right, let's keep going with this problem. The next thing the problem asks for is the test statistic. We're going to again go into regressions, simple linear. We're going to put x in and put y in and hit compute. Our test statistic is going to be down here next to our p-value, just like it was in the last chapter, but we're going to take the one that's for the slope, and that's on your resource sheet as well. So we want the t-stat for slope. Therefore, our test statistic is going to be 9.018. And notice they do give you the p-value. So if you didn't want to just check the test statistic versus the critical value, the other thing you could do is look at your p-value versus alpha. You can always do that. Okay, so let's go ahead and graph our two-tailed test here. My graphs are getting worse. And let's look at our rejection regions. So we are in the last slide, we found our critical values, and that tells us our our rejection regions. So if I'm anywhere in this red, either on the number line or in the shading, then those are my rejection regions. So on either side, and these are negative T naught and T naught. So we're going to take our data up here, the 9.018, and see where that would fit on the number line. Well, that fits way out here, right? If I try to see where this test statistic is, it's way out there. And so that's going to be in my rejection region, right? Because this rejection region is going to keep going. And therefore, I'm going to reject H naught. Now, the thing is, for the wording, we have to think about that a minute. We rejected the null hypothesis. Well, the null hypothesis is saying no correlation. So if we reject that, then that means that we do have correlation. So the null hypothesis was that there was no correlation. We rejected that. Well, if we reject no correlation, then we must have correlation. And so we're going to say there is enough evidence at the 5% level of significance to conclude that there is a significant linear correlation between the hours spent studying and the test score. And we were pretty sure that was going to happen because look way up here at the R. The R is very strong. It's at 0.954. So we could be pretty sure that we have a strong correlation, but we still have to test like this to find out if it's significant. All right, so let's jump to 9.2. So first we're going to try to match the graph to these equations. So my first equation is negative 1.361x plus 21.952. So remember that the numerical coefficient sitting by x, that's our slope. So we know because it's negative 1.361, we know that this line better be headed downward, right? And so our line is going to look like this. So that's going to rule out two of them right away. Now what we have to do is see which of these lines would hit the intercept or hit the y-axis at 21.95, excuse me, 9.59. Yep, so, oh, look at me. I wrote x-axis, but I meant y-axis. All right, so we want to come back to the y-axis being 21.952. Well, this graph, if we Let me see if I can draw this line backwards. If we draw this line all the way back to the y-axis, it is not at 21. It looks like it's maybe up at 26 or 27, right? If I come back to the y-axis, that's too high. The next graph below it has a positive slope. The next one on top is a positive slope. So let's look at this last one. If we look at where it comes back to the y-axis, it's probably about 21. I know it's not magic, but close. So it looks like this one would be 13. All right, so let's try the next one. The next one is 2.115x plus 21.958. All right, so we know that it either needs to be the bottom left or the top right because we know that it has a positive slope, right? The slope is 2.115. All right, so what we need to do is draw these backwards. Let's see if I can get this to work. So this one comes down to about 10. So that's not going to work, or maybe just a little below 10. That looks like that's the next one. This one, if I draw my line back, it looks like it's right about at the 21. So this one would be number 14 because it crosses the y-axis at about 21.958 and it has a positive slope. If I head over here to 15, it has a positive slope as well, 2.125, but it crosses around 10, and that looks like that one is right down here. So that's what you're going to do. You're going to look at the shape first, whether it's headed upward or downward. These are both lines. And then see where the line would come back to the y-axis. Okay, so another one from 9.2. We're looking at a table that has calories versus sugar, and they're looking at the caloric contents and the sugar contents of 11 different breakfast cereals. And first they want me to find the equation of the regression line. So I'm going to go ahead and go to StatCrunch. I'm going to do regression simple linear. And when I do that and put my X in and my Y in, when I do that, I get the estimates for the regression line. I get the slope and I get the intercept. So don't forget that the slope is going to be the numerical coefficient in front of X. So when I come down here to the slope, I get 0.21. Oops, look at me. I wrote that wrong. Let me see if I can get rid of that real quick. My eraser's not working very well. Let me see. Okay. So 0.21x, that's my slope. And then when I grab my intercept, that would be negative 25.69. So all I'm doing is grabbing the estimate here that StatCrunch figured out. And so that's the relationship. If I want to predict for other calories, I could do that using this equation. And we're going to actually do that. But let me show you something before we do that. The range of the x's. So my smallest x is 150, and my largest x is 200. So what happens with predictions is I have to stay within that range. I can't try to predict outside of my data range because I might be falsely predicting because I only looked at data in between that range. So if they try to get me to predict something less than 150 or more than 200, I'm not going to be able to do that. All right, so let's predict a few here. Okay, so I misspoke. We're going to pick a graph first. what happens at the very bottom, when you do regression simple linear, there's all this data on the first page. And then if you go to the little arrow on the bottom of all of that data, it will actually show you the graph, which is right here. It'll show you the graph with the dots, and it'll also show you a line through that. So your best fit line. Now, unfortunately, we can't control the scale, so you notice the scale from MyMathLab looks a little different than, because MyMathLab's going from 120 to 220 here, and this one's going from 150 to 200. So it looks a little off, but hopefully it's close enough that you can fix, where did I get the word fix? You can find which graph it is, and so in this case it would be B. Okay, now let's predict. Okay, so before we predict, let me just remind you that I need to stay within the range of x's. And so the 150 was the smallest and 200 was the largest. So I can't be less than 150, I can't be greater than 200. So the first calorie count they gave me was 160 calories. So what I did was I took 160, I put that in for x, because remember our regression line looked like this. Okay, so I substituted 160 directly in for x, put it in my calculator, and I got 7.91 back out. Okay, that's great. So that's 7.91 grams of sugar. And I'm good to go. I can go to the next data point. Well, the next data point they asked me for was 90 calories. Well, 90 is outside of my range. Of x's. Therefore, this is not meaningful. I cannot predict, because 90 is outside of the data that I was looking at. I cannot try to predict a value of y. So I'm just going to click B, saying it's not meaningful because it's outside of the range, and I'm going to move on to the next. All right, so let's try another problem. All right, this is 9.3. We've got the average weekly wages for the state and the average weekly wages for federal. So the state is our X, the federal is the Y. They went ahead and gave us the regression line. That was fine. But then they ask for R squared. So we're going to go ahead and click our StatCrunch box next to the data. We're going to again do regression and simple linear. The R squared is right here, right under the correlation coefficient. That was very nice of them to give that to us. Thank you, StatCrunch. And therefore we get 0.956. Now the coefficient of determination, the R squared, just tells us the fraction of variation that is explained by these two variables, by the relationship of these two variables. And when we answer this, we're always going to use the y description first, the variable y. So it says here, the coefficient of determination is the fraction of the variation in average weekly wages for the federal government employees. So we always use y first, because the way we find R squared is by using y's, if we made you do it by hand and not use StatCrunch. So it's the average weekly wages for federal government that can be explained by the variation with the state data. Okay, so it's always going to be the variation of y that can be explained by x. Remember, x is our explanatory variable. That is the variable that's explaining what's happening with y, if we have a good setup. This is R squared. So R squared is going to be the explained portion, And then 1 minus r squared is going to be the unexplained. And the unexplained are things like coincidence. It could be sampling error. We didn't pick a good sample. It could be that another variable is affecting this data that we didn't look at. So lots of things can happen in the unexplained. You really want a pretty large explained, or you probably need to go back and look at your data, look at your sample, and look at your variables. All right, this problem has one more step. The next part, they asked for the standard error of estimate, and that's an S with a little e. That is right here. Remember, this is also the standard deviation. Okay, and so that's right under the r squared, and that would be 23.97. When we go to interpret the standard deviation or the standard error of estimate, whichever way you want to call it, we again always use y first. So the standard error of estimate for the average weekly wage for the y variable, which is the federal government employees, for a specific average wage for the x variable, which is the state government employees, is about $23.97. Okay, but we always put y first. So the standard error of estimate for the y variable for a specific x value is about $23.97. Okay, so just remember to do y first. Okay, so here's the last one for 9.3. We're looking at data. We've got average weekly wages in dollars for state government employees and federal government employees for 10 years. And we want to construct a 99% prediction interval. So this is kind of like a confidence interval. It's going to have the two endpoints, just like a confidence interval. But when they ask us for a prediction interval, they give us a data value. So for this one, they want a 99% prediction interval for x equal $823. Supposed to be 4. So a 99% prediction interval for x equal $823. We need that. We're going to use that in just a minute inside our StatCrunch. But what we're going to do again is hit this box for StatCrunch so that we make sure all of our data comes into StatCrunch so that it can do all of its analysis. So let's look at StatCrunch on the next page. All right, once you pick or click that box and then go to regression simple linear, you're going to put your x and y values in just like you were doing already, but then you have to come all the way down here to the bottom, and you don't see it at first, but you have to come all the way down here. You're going to put your x value of $823. You're going to put your significance level of 99% or 0.99. And then you're going to click compute. So right as soon as you hit compute, you get lots of data, right? You get the correlation coefficient, the r squared, the estimate of the error. You get your regression line. You have to come all the way down to the bottom. If you come all the way down to the bottom, you will get your prediction interval here. We don't want the confidence interval. We want the prediction interval. So go to that last column, and that's going to be the data that we need for our answer. Again, StatCrunch does all the work for us. Okay, so we've done all our work. We know that we're doing a 99% prediction interval for the weekly wages of $823. Now, when we pick which box we're going to use, we don't take chances. We want to be confident. Okay, so we're going to be 99% confident that when the average weekly wages of a state government employee is $823, then the average weekly wages for the federal government employee will be between, this is where we're going to grab our data from StatCrunch. So we've got 1,861.61. They ask us to do to the nearest cent, so that's 2 decimals. That's my lower boundary for my prediction interval. And then in the top, I'm going to put 1,239.05. Okay, that is my prediction interval. I've got my lower endpoint and my upper endpoint, and that's tied to an x equals 823.